Hello everyone. So today I'll be presenting my work on compressing unit vector correlations via Sparse Pseudorandom generators. And this is joint work with my collaborators, Amit Agarwal, Urbana-Champaign, and my peer. So let me first start with the motivation. So a popular paradigm these days in MPC is so-called offline-online MPC paradigm, or also known as the pre-processing model. So let's say Alice and Bob want to compute some function f securely on their private input section. So what we do is we divide the overall protocol into two phases. The offline phase, where the inputs are not known to the parties. So parties use random inputs and interact to generate so-called correlated randomness. And then we have the online phase where the inputs to the parties become known. And then they consume the correlated randomness that they generated in the offline phase to securely compute the function f on their private instance. Now, some form of correlated randomness that you might have come across is d4s triples and OT correlations and so on. Okay, so this paradigm of offline-online MPC is very similar to how we actually consume electric energy in modern world. So where factories burn coal to produce electricity, and this electricity can be thought of as the pre-processing material that gets consumed in a household for different utilities. So you can think of consumption of electricity as the online phase. Why do we do this? For the same for getting online efficiency. So you, as soon as you press the button, the switch, you want the night lamp to turn on. So this is also the reason why we do offline-online MPC, because it boosts our online communication and traffic. I mean, it reduces our online communication. Furthermore, there is also opportunity to do batch optimization for the offline phase, where we can generate large batches of correlated randomness with communication, very low communication. Okay, so now let me define more formally what is the notion of correlated randomness. So correlation is defined with respect to some public distribution D. So we have some distribution D, and we sample an element R from this distribution, and simply additively secret share this sample among the parties. This is described in this picture. So we sample R from this distribution and secret share it between the parties. And one example is if you define a distribution to be a uniform distribution of triples A, B, and C, where C equals A times B, then the induced correlations. Then the induced correlation would be what we know as d4s2-2, triples. Okay, so what is the main challenge in offline-online space? So the main challenge is how do we efficiently generate and store many instances of such correlated randomness. So let's say you want to generate 1 million d4s. How do we efficiently do this? And how do we efficiently store this correlated randomness? So an interesting line of work was started in this paper in 2018 by Paul and then follow-up work in 2019, where they constructed this object for pseudorandom correlation generators for some so-called correlations such as vector OAE, OT, and sub-related correlations by leveraging the LBM assumption. Now let's see what this object pseudorandom correlation generator, PCG for short, really is. So think of a PCG as a distributed form of a standard PRG. So here we have a gen procedure, PCG.gen. It generates two short correlated seeds and distributes it to the parties. So now parties are holding two short correlated seeds that they can non-interactively or with low communication expand into long forms of correlated pseudorandoms. And the major benefit here is that communication efficiency. So during the expansion procedure, the communication of this expansion procedure is sublinear in the length of the output correlated randomness. And sometimes it's even silent, which means you don't have to do any communication at all. It's completely local. So let's say the length of our output correlated randomness is n. So for correctness, what we apply is that the joint distribution of the outputs of the expansion procedure of both parties is computationally indistinguishable from an additive sharing of fresh sample R from n copies of your distribution of interest. For security, we require that, let's say Alice is there, then the joint distribution of Alice's seed and the expanded output of the honest party, Bob, should be indistinguishable from the joint distribution of the seed of the correct party and a reverse sampled output of the honest party. Okay, so coming back to our analog to electricity. So think of PCG as being these short batteries or capacitors that can store a lot of energy or correlated pseudorandomness. And when you need it, you can just expand it and consume the electricity or the correlated randomness. So this has a dual benefit. So you can generate lots of correlated pseudorandomness very efficiently. And also storage, you can store them. Like these seeds are much shorter than the output. So you can store these correlated pseudorandomness in a very efficient way. Okay, so there are some limitations of existing works, which is that efficient PCGs are limited to simple correlations such as triples, random OT correlations, and OE. And if we want to extend this to much richer correlations, that is possible, but currently it is practically inefficient. So in this work, we provide a practical PCG for a useful correlation, which we call unit vector correlation. We'll see shortly what this is. So recall this slide from, recall this figure from my previous slide, where I defined what is a correlation. So the correlation is defined with respect to some public distribution, and basically parties are holding shares of some sample from this distribution. Now, if this distribution is the uniform distribution over all unit vectors of a fixed length, let's say length is 100, and a uniform distribution over all unit vectors of length 100, then the induced correlation is what we call unit vector correlation. In other words, parties are holding additive shares, RARB. If you add them up, you will get some random vector R, meaning that the non-zero location in this vector is random, and it's unknown to any of the parties. Okay, so in terms of applications, these unit vector correlations are very useful in doing secure lookup table evaluation. So let's say you are doing GMW style PC. So usually we do add like multiplication gates and addition gates. But now you can also support lookup table gates. Let's say where you have a public table of size, let's say 100, and you want to look up an index where the index is secret shared between the parties. And you want a secret sharing of the value items. So you can do such secure lookup table evaluations with just one element of communication between the parties. This also allows you to do online optimal PIR in terms of communication. PIR stands for private information retrieval. And these kind of correlations also sort of provide a middle ground between FFT style generic MPC and OT style generic MPC by agent. So if you think of the communication computation trade-off, FFG enables you to do generic MPC with optimal communication, meaning the communication doesn't depend on the circuit size. But the computation is very heavy. Whereas OT based GMW style MPC lets you do generic MPC with low computation cost, but communication scales linearly in the circuit size. And what I'm saying is that these unit vector correlations, which I'll call UV correlations for now, they allow you to do MPC with slack communication sublinear in the circuit size, while only having a moderate amount of computation. So now the question is, how do we efficiently generate and compactly store many independent instances of such correlations, such UV correlations? So let's say you want to generate 1 million random unit vectors and share it between the parties, or 1 million random independent unit vectors. How do we generate such correlations and store it? Basically, we want to design a PCG for this correlation. So there is this framework from Triworks, which is termed as PRG plus HSS framework that I described. So let me first start by describing what each of these components are. So we all know what a PRG is. It takes in a uniform CS and expands it into a long pseudorandom string R. Okay. What is HSS? Homomorphic secret sharing. So you might have seen this in some of the previous talks. So let's say you have an input X. Then HSS allows you to secret share this input X among 2 or more parties. And then parties can do homomorphic validation of a function on their shares to compute output shares, so that when you add the output shares, it equals the function applied to the original. So this is a kind of distributed form of FHE. Okay, so what is the PRG plus HSS framework? So what I'm saying is that you can, if you have these two objects, PRG and HSS, in a straightforward way, you can combine them to get a PCG for any additive correlation. So what you do is the following. So you take the state of the PRG sets and then use the HSS share procedure to secret share the state between the two parties. And this would be a gen procedure of the PCG. Okay. Now parties can do a homomorphic evaluation on their shares with respect to some function. And the specific function that we fix in this case is the PRG expansion procedure, that green triangle, composed with this rectangular box, which is a function that maps uniform distribution into the distribution D that you are defining your correlation over. So this is the function that you evaluate homomorphically using HSS, and the output that you get, the parties get, form an additive share of the correlation with respect to the distribution D of difference. And now you can think of this procedure, the blue triangle, as a PCG expansion procedure. So this is a general framework, and using this you can get a PCG for any additive correlation. But there are some downsides. So the downside is that evaluating this function F is quite costly inside of physics. Why? Because this rectangle, the purple rectangle, is a high degree computation. Mapping uniform distribution into a non-uniform distribution. In our specific case, this unit vector distribution is a high degree computation, which is why it becomes practically inefficient. So our solution to this problem is to design a low degree equivalent of this composed function F. So if we can design a low degree equivalent of this function, then evaluating it inside HSS would be efficient. And this low degree equivalent of this function is what we term as a sparse pseudorandom generator in our book. And I will define what this is. Okay, so here I am showing the difference between a standard PRG and a sparse PRG. So focus on the left for the start. So on the left we have the standard PRG. It takes in some C, expands it into uniform, pseudo-uniform sets. On the right we have a sparse pseudorandom generator. So it takes in some C and expands it into a sparse pseudorandom distribution. And in this specific case, the sparse distribution is defined as the following. So every block, let's say in this case block of size 4, would have exactly one non-zero location. This block would be a parameter, also called the sparsity parameter in our book. So you can fix the sparsity parameter to be anything that you want. For example, if you want unit vectors of length 16, then the sparsity parameter would be 16. So this is how we define a sparse pseudorandom generator. Okay. So looking at basically, we would execute this kind of sparse pseudorandom generator inside HSS to get a PCG for the unit vector correlation. Okay. So for this to be efficient, we will also need this sparse PRG to have low DD. Or what does DD mean here? So think of each output bit of this sparse PRG as a multivariate polynomial of the seed bits. So we want the total degree of this polynomial across all the output bits to be minimized. Okay. So how to construct such sparse PRGs? Yes, there are some approaches that you can try. For example, just take any standard PRG and map the uniform output bits to a uniform sparse distribution. As we discussed, the caveat is that this increases the overall degree of the PRG because this mapping is a high degree computation. Something else that you can try is try to supply a standard PRG with non-uniform seed bits or sparse seed bits and hope that you would get sparse output bits. And turns out that the caveat here is that the pseudorandomness doesn't seem to put in. Okay, so the approach that we take in this work is to leverage so-called non-binary local PRGs. So I'll define what this is. So first we move from binary PRG keys to non-binary PRGs. What are non-binary PRGs? So now the inputs and outputs of the PRG would no longer be bits. They would be symbols from some alphabet of size greater than 2. In this specific case, let's say alphabet size is 4. And the symbols are just 1, 2, 3, 4. So our seed would have some random symbols. And the output would also be a sequence of pseudorandom symbols from the alphabet. So as a first step, what we do is simply, if we encode the output symbols of such a non-binary PRG sparse format, and the sparse format in this specific case would be the unit vector representation of each symbol, also what some people call as one-hot representation, which means that let's say we look at symbol 2, which is the first output symbol, then we turn on the second location as 1 and rest as 0 and so on. So if you look at the last output symbol, which is 4, that means that the fourth, like the last block on the right, would have 1 at the fourth location and 0 everywhere else. So each symbol is getting mapped into a block. The size of the block is equal to the size of the alphabet, and the encoding is this unit vector encoding or the one-hot encoding. Okay. So by doing this, we get correctness and pseudorandomness directly for this diagram on the right. So it means that all our outputs are unit vectors, and the location of the non-zero location is also pseudorandom because that directly corresponds to the symbols of our non-binary PRG. But it's not clear what the degree of this PRG that we constructed on the right is. In fact, it can be as high as like the length of the seed. So to get a low degree sparse PRG, what we do is we enforce another property on the underlying non-binary PRG, which is called small locality. So locality means like the number of output symbols, the number of inputs, how many input symbols affect a given output symbol. So for example, in this diagram, the output symbol 3 is getting affected only by 2 input symbols. So the locality in this case is exactly 2. So the observation is the following. Given such a PRG which has small locality, if you encode the seed input symbols also in a sparse format, So in the previous slide, I encoded the output symbols in the sparse format. What I'm saying now is that if you additionally encode the input symbols of this state also in a sparse format, then you get a low degree sparse PRG. And I'll try to explain this in a bit more detail in the next slide. So here is how we get low degree thing. So let's say you have the local, the PRG, small locality on the left, right? So here Z depends on two input symbols, X and Y. So Z, think of it as a variable, which is some local function f, like two input variables, X and Y. Okay, so now we can represent f of X, Y as this expression on the right, where you check whether X is 1 and Y is 1. If so, the output is at 1, 1. Or if X is 1, Y is 2, output is at 1, 2, and so on. Now, what I'm saying is that if you see on the right, I have encoded the symbols on the left in sparse format. And so you can rewrite this expression, which has equality checks in a low degree format. So where X equals 1 is just replaced by X1. And Y equals 1 is replaced by Y1 and so on. So this last expression that you see is low degree, and the degree here is exactly 2. So in some way, if you have a PRG, local PRG with locality D over some aggregate sigma, and you do a sparse encoding of the input and output symbols, you get a degree D sparse PRG. Where sparsity parameter is the size of that, right? I mean, your blocks would be of size equal to the average size. And then you can plug it into an HSS for computing degree D polynomials to get PCG for unit correlations. And there are different ways you can instantiate this HSS. In the information theoretic setting, you can use BGW style multiplication on shares to get. So if you have, let's say, B times T plus 1 parties with T corruptions, then it allows you to do B minus 1 multiplications non-interactively. Also in the 2-party 1 corruption case, which is the, you can use computational HSS based on PCR and from frameworks and UR assumption to instantiate this HSS. So some further optimizations. Let me just quickly go through this. So in the paper, we saw that the PCB sleep size can be further compressed using what we call the multiplicative DTF. That means that output shares. So DTF is something that you might have seen in prior works. This tree-based construction for compressing unit vectors, but a single unit vector, not multiple unit vectors. So if the output shares of a DTF form a CNF sharing, then you can do multiplications non-interactively. And so we show that you can construct this form of multiplicative DTF. And this is an improvement over a prior construction in the 3-by-1 correction phase. And this helps us in reducing the PCB sleep size from K times B, where K is the number of local PRG seed symbols, and B is the size of the aggregate, to lambda times K times log B, where lambda is some secret parameter. And other applications of this multiplicative DTF is other application is that it allows you to search a document that contains all D keywords using this T plus 1 non-correlating servers, whereas TLS construction require two quality non-correlating servers. Also, we show that we can support HSS with just multiplicative reconstruction instead of additive reconstruction. Note that most HSS schemes in the literature have with additive reconstruction require solving distributed D-log for every multiplication, and this forms a bottleneck. We show that a variant of UD correlation, which we call weight one correlation, where the non-zero location is a random value, can be generated using HSS with just multiplicative reconstruction, and this allows us to use the deviant style HSS or subgroup decision-based matrices without going into the distributed, without using the distributed law. And this variant of UV correlation, which is weight correlation, can be converted into standard UV correlation with local mitigation. Okay. Since I'm running out of time, I'll just go through this. So in the paper, we show different candidates for this non-binary local PRG that we need for our construction. So we show that first of all, any local binary PRG can be used to construct local non-binary PRG by just running multiple copies of the line pattern. In the paper, we also made some new construction for local non-binary PRG, which we call Sparse Pseudorandom candidate, and this is an FFP-friendly candidate inspired from a combination of sparse LP and standard LP. Okay, so we also show that it can support variants of UV correlation, such as authenticated UVs, lookup table correlation, tensor correlation. You can see this in the paper. We also gave some cost estimations in terms of seed size, throughput. Throughput means how UV vectors can generate in a second, and compression rate. Okay, so maybe if someone is interested, I can come back to this. Thanks. So this picture gives like the entire thing of the entire area of XSLs, local PRDs and PCGs and applications that we explore in this paper. It's not upon yet, we put it through. And thanks. So yeah, I'll wait.